Welcome to another video. Today, we're diving deep into a cornerstone of chemical equilibrium, Châtelier's principle. We're going to go on a journey from the very basics, the stuff you can feel intuitively, all the way to the heavy-hitting thermodynamic concepts you'd need for something like the Chemistry Olympia. So let's jump right in.
Here's the game plan. First, we'll start with the core idea, what it means for a system to be under stress. Then, we'll get into the nitty-gritty of how equilibrium actually shifts, and we'll pay special attention to temperature, because it's a bit of a special case. After that, we'll uncover the deep thermodynamic reason why this whole principle even works. And finally, we'll see how this isn't just theory, it's chemistry that literally shapes our world every single day. All right, let's kick things off with Section 1, a system under stress. Before we can understand how a system reacts when you push it around, we first have to get a really clear picture of what it looks like when it's perfectly happy and balanced.
Now, the one word here you really need to latch onto is dynamic. A system at equilibrium is not frozen. It's not like everything is stopped. Oh no! The forward and reverse reactions are still going like crazy. The magic is that their speeds, their rates, are perfectly matched. It's kind of like a perfectly balanced seesaw. It looks still, but the forces are absolutely still at play.
And that, of course, brings us to the man himself. This quote right here is the absolute heart of the principle. The best way to think about it is that chemical systems are kind of lazy. They want to be in their most comfortable state, their lowest stress state, which is equilibrium. So if you go and poke it, say by changing the concentration, or the pressure, or the temperature, it's going to shift around and adjust itself to cancel out whatever you just did. It's the fundamental stress response of a chemical reaction. So we've got the core idea down. Now for Section 2, where we get practical. We know the system is going to shift to relieve stress, but which way? Left or right? To predict that, we need a tool, a way to measure just how far off balance the system is. And that tool is the reaction quotient, Q. Okay, think of it like this. K, the equilibrium constant, that's your destination. It's the perfect, blissful ratio of products to reactants that the system is trying to get to. So what's Q? Q is your current GPS location. It has the exact same formula as K, but you plug in the concentrations you have right now at this very moment. And by comparing our current location, Q, to our destination, K, we know exactly which way we need to drive.
And the rules for reading the GPS are just incredibly straightforward. If your current ratio, Q, is less than the target ratio, K, well, that just means you don't have enough products yet. So the system shifts to the right to make more. On the flip side, if Q is bigger than K, you've overshot the mark. You have too many products, so the system shifts back to the left to use some of them up. And if Q equals K, you're there. You're at equilibrium. No net shift. It's that simple.
Okay, let's put this into practice. Here's a classic, the synthesis of ammonia. Now, take a look. On the left, the reactant side, we have 4 moles of gas, 1 nitrogen plus 3 hydrogen. And on the right, the product side, we only have 2 moles of gas. So what happens if we take this system when it's at equilibrium and we just squeeze it? We decrease the volume.
Well, when you decrease the volume, you're stressing the system by jacking up the pressure. All those gas molecules are suddenly crammed into a smaller space. So how does the system fight back? How does it relieve that stress? It tries to reduce the pressure. And the easiest way to do that is to have fewer gas particles bouncing around. So the reaction shifts to the side with fewer moles of gas. In our case, it shifts hard to the right, going from 4 moles of gas down to 2, cranking out more ammonia to relieve that pressure crush.
Now this is a classic trick question, so let's pay close attention. What happens if you add an inert gas, something like argon that doesn't react? The answer, and this is so important, depends entirely on the conditions. Let's look at the left. If your container has a fixed, constant volume, adding argon increases the total pressure. But the partial pressures of your reactants and products, they don't change. They don't even notice the argon is there. So Q is unchanged, no shift. But now look at the right. If you add argon and you want to keep the total pressure constant, the container has to get bigger. The volume has to increase. This lowers the partial pressures of all the reacting gases, and the system will shift to the side with more moles of gas to try and push back and bring that pressure up again. It's a really subtle but absolutely vital distinction.
Moving right along to Section 3. Here, we're going to talk about a totally unique kind of stress. See, everything we've talked about so far, it's about knocking the system off balance and then letting it return to the same equilibrium point, the same K value. But temperature is a game changer. It is the only stress that actually changes the value of the equilibrium constant itself. It doesn't just push the ball up the hill, it completely reshapes the valley floor.
The absolute easiest way to think about this is to just treat heat as if it's a reactant or a product. For an exothermic reaction, heat is given off, right? So just imagine heat is written on the product side of the equation. If you add more heat by cranking up the temperature, it's like you're adding a product, so the reaction shifts left to use it up. For an endothermic reaction, heat is absorbed, so it's like a reactant. Add more heat and you push the reaction to the right to consume it. The system always fights back to counteract the temperature change.
And this isn't just some handy trick, it's grounded in hardcore thermodynamics. This beast right here is the Van Hoff equation, and it's the mathematical proof. Now don't panic, you don't need to memorize it for most things, but you have to understand what it's telling us. It directly connects the change in K to the change in temperature T, and it all depends on the reaction's enthalpy, delta H. This is the math that proves our simple heat as a product rule of thumb is actually correct.
Okay, so we've covered the what and the how. Now for section 4, the deep thermodynamic why. I mean, why do systems even bother returning to equilibrium in the first place? Well, the ultimate reason, the driver behind everything we've talked about, is a concept called Gibbs free energy.
This is such a great way to visualize it. Imagine the progress of a reaction as a ball rolling along the floor of a valley. Equilibrium is that one spot at the absolute bottom, the lowest possible point. Now, any stress you apply, adding a reactant, changing the pressure, is like giving that ball a shove up the side of the valley. Its Gibbs energy goes up. And what does any ball on the side of a hill or a valley do? It spontaneously rolls back down to the lowest point. That's exactly what a reaction does. It shifts until it finds that point of minimum Gibbs free energy all over again. And here it is. This is the master equation that governs that entire energy valley. Delta G, the change in Gibbs free energy, tells us if a reaction will happen spontaneously. Think of it as the steepness of the valley slope. The key is that RT ln of Q part. When you're not at equilibrium, Q isn't equal to K, and that term makes delta G non-zero. The ball is rolling. The system only stops shifting, it only reaches the bottom of the valley when Q finally equals K, because that is the one and only condition that makes delta G equal to 0.
All right, for our last section, let's pull all this theory out of the textbook and into the real world, because this stuff isn't just for exams. These principles are the actual control knobs for some of the biggest and most important chemical processes on the entire planet. And there is no better example, period, than the Haber-Bosch process. This reaction literally pulls nitrogen gas out of thin air and turns it into ammonia, which is the backbone of all modern fertilizers. It's not an exaggeration to say this one reaction feeds billions of people. But look at it. It's exothermic, and it reduces the number of gas moles, which creates a fascinating puzzle for chemical engineers. This table just perfectly captures the central conflict at the heart of industrial chemistry. Châtelier's principle tells us exactly what to do for the maximum possible yield of ammonia. Use low temperatures because the reaction is exothermic, and use super high pressure because you're going from 4 gas moles to 2. But here comes the reality check. In the real world, a low temperature means the reaction is painfully, uselessly slow, and ridiculously high pressures require equipment that's incredibly expensive and dangerous to run. So, the solution is a compromise. It's a carefully chosen temperature and pressure that finds the sweet spot, balancing how much you make, how fast you make it, and how much it costs. It's a beautiful trade-off between what thermodynamics wants and what kinetics will actually allow.
And you see the same logic all over the place. The contact process, which makes sulfuric acid, faces the exact same compromise between temperature and pressure. The Solvay process is another really clever application. To keep making their product, they just keep adding more reactants, and at the same time, they pull one of the products out of the solution by making it precipitate as a solid. This keeps Q really low and just forces the reaction to keep chugging forward to the right.
So before we wrap this up, let's just quickly bust a few common myths. First, catalysts. Yes, they're super important in industry, but they only affect the speed, how fast you get to equilibrium. They speed up both the forward and reverse reactions equally, so they never, ever change where the equilibrium position is or the value of K. Second, remember our inert gas rule? It only matters if the volume can change. And finally, keep in mind Châtelier's principle is a qualitative tool. It's fantastic for telling you which way things will go, but if you need to know how much they'll shift, you've got to break out the calculator and do the full equilibrium math. And that brings us to one final challenge for you. We're looking at the equilibrium between dinitrogen tetroxide, which is a colorless gas, and nitrogen dioxide, which is a brown gas. The forward reaction, going to the right, is endothermic. It absorbs heat. So here's my question for you. If you take a sealed tube of this gas mixture and plunge it into a beaker of hot water, what are you going to see? And more importantly, can you explain why, using everything we've talked about today? Think about the stress, think about the enthalpy, and think about which way the system's going to shift to fight